on that. So if you want to ask questions during the talk, I'd prefer that if just jump right in. And so I noticed it because sometimes I notice the chat screen, sometimes don't. I don't want to miss any questions that way. So with that, I think you can see my screen, right? The talk. Okay, awesome. So thank you very much for inviting me to the to do the first of the Zangwill seminars. I'm very happy and honored to be here, and thank you all for being here at different time zones. Either it's late Friday evening or early Friday morning. So thank you very much for that. The work I will present today is joint work with two mathematical psychologists, Danielle Navarro and Joachim Vandekerkhoff, and my statistician colleague, Erkan Buzbaş. Erkan is joining in. So if you have any questions about the technical aspects that is a little bit maybe too complicated for me, he might just jump in and answer some questions as well as necessary. So the title of the talk, as you see, is the case for formal methodology in scientific reform. At the end of the presentation, I think I can share this PDF with anyone who's interested. I have the link to the preprint and everything as well. So this talk in the paper was, was motivated by some observations we made about the scientific reform literature in the last decade, which started as this replication crisis, which was triggered by a realization of some symptoms, including unsound research practices, especially in experimental sciences. A lot of disciplines have experienced difficulty with low reproducibility of scientific results, and there have been issues with transparency in science reporting as well. And one of the precursors, maybe, of this reproducibility crisis is often believed to be, or at least presented as, this Ioannidis article that you will also see on the Wikipedia page for the replication crisis from 2005, why most published research findings are false, which is very interesting because as later I will talk about the fact that the relationship between reproducibility and the false results or true results is not as straightforward as it might seem. So the realizations about what's going wrong in science then triggered kind of an increasing interest in meta science or meta research, an increasing number of claims about how science works and how science actually should work, and also a lot of fast-paced changes in science policy and practices. And in this, in the midst of this ongoing reform, we noticed a few things that we thought were potentially a little bit troublesome, maybe. One of those things was about each of the claims that have been proposed about how science should work or how we need to change our methods and practices. There has been a lot of back and forth argumentation, right? A lot of opinion pieces, a lot of commentaries. As you will see in this example here, even the idea that there's a replication crisis has been contentious. There have been a lot of pieces written about, no, this is not a crisis, or yes, this is a crisis. Those who say that this is not a crisis are wrong for these reasons. And, a lot of this discussion and debate. What we don't see in a lot of these cases is a lack of formal arguments whenever they are necessary. That is, whenever we're talking about statistics or methodological practices. And also another thing that we notice is that there has been a lot of rush to change policies in scientific practice. An example of this is this Journal of Basic and Applied Social Psychology. 5 years ago, they decided to ban p-values because of as a result of this replication crisis. They thought it would be a better practice, which was then shown to be, at least argued to be, a little bit problematic by statisticians. And last year in the American Statistician, this article came out that discusses that after the ban, a lot of the articles did not provide enough information to be able to judge their claims, and the authors were still overstating their claims for the most part. So the journal has not yet backed down. The editor seems to be still standing behind the decision to ban p-values, but it's not clear what the use of this policy has been. The problem or problems that we see in this picture is similar to the practices that have been originally criticized by scientific reform, such as proposing some untested or unestablished methodological innovations as solutions to reproducibility problems. A lot of taking suggestive statements about methodological tools and presenting them as bold, general and unconditional facts about science. Sometimes using vague and even misleading statistical statements to provide support for some of the claims and some of the tools that are being proposed. And also, from our perspective, from a more statistical and formal perspective, an overall lack of rigor in part of this new effort in method development. So the back and forth argumentations and proposals and commentaries and rejoinders and counter arguments, they all have a place in scientific discourse, of course, but we believe that they should be employed when we do not already have sounder and better and well-developed processes in place to resolve some of the existing arguments for good. And formalism is this process that already exists for to show support for methodological claims. So when we're talking about what a p-value is, this is not necessarily a matter of discussion. We know exactly what it means. So we need to refrain from repeating the same mistakes of the past. And we don't want to be creating new scientific processes that are not necessarily better than the ones that they replace. So in this talk, first I'm going to introduce this idea of formalism, what we mean by it and where it applies, what it entails. Then I will illustrate how to implement our idea of formalism in the existing reform literature by focusing on 3 specific claims that have been published and repeated many times in the literature. First one is that reproducibility is the cornerstone of or a demarcation criterion for science. Second one, using data more than once invalidates statistical inference. And the third one is that exploratory research uses wonky statistics. For the first 2 claims, I'm going to provide some formal evaluation of these claims and present some results and maybe resolve some of the existing debates. And for the last one, I'm just going to be able to discuss some challenges in formalization and what that means and why that still matters. Let's take a look at what we mean by formalism. So first, it is important for us to acknowledge that the scientific reform comes with many claims about scientific practice. Not all of them are relevant for the purposes of this work. What we're talking about or what we're focusing on are methodological claims, which we define as statements about scientific methods that are either based on statistical arguments or supported by statistical arguments, or claims that impact statistical practice. So an example is, p-hacking or robust methods or exploratory data analysis. Those things would be relevant for methodological claims. Whereas if we're talking about whether we should share everything about the research process, kind of transparency initiatives, or whether registered reports is a good publication model, those are not necessarily methodological claims within this framework. What we specifically mean by formalism is that claims about methodology need to follow from probability calculus to be valid, and this validity is only established by proofs, either by mathematical, analytical proofs, or simulation proofs. before they can be applied safely or before they should be allowed to impact policies and practice. Where does this idea of formalism come from? It comes from formal sciences like mathematics and computer science, logic, or statistics is, of course, one of those. Let me just give you a familiar example from the history of statistics to illustrate this idea. Central limit theorem, which is probably the second most important result in probability theory after the law of large numbers. What you see in this picture is quincunx, which is also known as a Gaussian board. You may have seen different versions of it, like the the simulation versions or the real life versions. This one probably you did not see before because Arkan and I built this one from Snicker bars and M&Ms and peanut butter, the Reese's cups, for a meeting with the statistics club on campus. Although it's a little bit flimsy and, like we really did not measure things, it was just very eyeball things. It still works. What you see with those M&Ms down there is pretty close to normal distribution. What the Gaussian board is supposed to show is that it does demonstrate the normal approximation to binomial distribution, which is the one form of the central limit theorem. Basically, the central limit theorem says that the sampling distribution of the mean or sums of independent variables converges to normal distribution as the sample size grows, regardless of the distribution of the original random variable. So the idea of taking a binomial random distribution and finding a normal that it converges to a normal probability distribution goes back maybe to 300 years to Demoir, like we showed in one of the first versions of this and conjectured that this is what's happening, which was a finding that was kind of lost in obscurity, and until almost a century later, Laplace, another French polymath, came across Demoir's findings and proved one of the first versions of the central limit theorem. Then over the years, from Lyapunov, who extended this to independent but not identically distributed random variables, to Polya, who actually gave the theorem its name, central limit theorem, for the first time. There has been a lot of statisticians, mathematicians working on this, trying to extend this finding, trying to test the assumptions, release the assumptions, maybe add more assumptions, and show that under which conditions this applies, how much it can be extended, until maybe in the 50s, then we see even more extensive versions of this that apply to other alpha stable distributions and the normal distribution even. And currently, when we talk about central limit theorem and why it's so central to the practice of statistics, is any scientist who ever employs a z-test or a t-test is actually using this idea whenever we don't know our variables are distributed normally. We make that assumption because we can make that assumption because typically we're working with means. So when you read statistics journals, typically this is the kind of work that you see. Some initial proofs, someone else taking this work, extended it, someone else showing that it works or doesn't work in other situations. A lot of proofs, a lot of math, a lot of robustness tests over time. So if we want to provide an outline for this kind of formalism, it may look like something like this, a structure of an outline. First, we have an idea, we conceive an idea, which may be similar to, like I have a binomial trial here. I have, like the coin tosses, for instance, and how do I formalize this? Then we need to define our variables, define the parameters and the model that generates the data. Then we have a formal version of a problem statement. And then after that, we need to make sure that this problem statement or a claim that we're making holds. So we need proofs. That's the stage 3. We need either mathematical proofs or simulation proofs whenever analytical solutions are not available. Then after that, we are able to demonstrate that this idea works with examples, practical examples that are used maybe in practice. And at the same time, others or same mathematicians are going to take this work, they're going to extend it, they're going to test its limitations, and maybe adjust the assumptions. Only after that, we get to the stage of practice in policymaking. So one of the things that we observe in the methodological reform is a jump from stage 0 to stage 5, and none of the work in between is shown. In many cases, I don't want to overgeneralize, but the claims that we're going to evaluate today are examples of that. So this immediate urge for implementation in our minds is a potential problem that can be addressed. So we show how to implement this formal approach to some meta-scientific claims, and I hope to illustrate that we can show the difference that it's going to make if we take this kind of approach whenever necessary. We start by laying out the groundwork. So I said that the step one is the definitions. What do we mean by definitions? So I can summarize it maybe under these 3 categories. So first we have, we need to state our regulatory conditions to establish a mathematical setup over which we can build and prove our methodological claims. So this is that's going to give us the guarantee that our proofs are gonna work in a well-developed setup. Then we need to state our assumptions about which requires us to identify our variables, the parameters, the constants, the model generating the data, and the limitations under which our claims should hold. And only then we get to properly define what we mean. And in this case, I'm gonna show you what this looked like for us, and only then we get to define one of the key concepts to our analysis in this paper. So at this point, I have quite a few appendices that I included in the slideshow. So I'm going to use these buttons to go back and forth between the appendices. The appendices are technical, so I'm not going to spend a whole lot of time in the appendices, but I want to be able to show you what the mathematical aspects of this work looks like, and then we can come back to the slides and talk about them in plain English. So when I jump into this first appendix, we see that we'll list our regulatory assumptions, regulatory conditions that include, like for all random variables, we have continuous non-degenerate distribution functions, things like that, a lot of notation. Then we have certain assumptions, because we're going to work with concepts like testing and results and reproducibility. So we need to first define what do we mean by a study, because we need a unit of analysis to be able to talk about reproducibility. So before we can even define what a study is, we need to set certain assumptions. For example, the first assumption, A1, is we assume that a true probability model generates data that we observed. Or if we look at this last one, A6, we define what we specifically mean by a statistical result. Only after setting these assumptions, we are able to define what we mean by a study. Obviously, this is an idealized version of a study, but it's a useful concept, and we can specifically identify its components, which in this case, we have the model under which we are making the assumption. We have the parameter of the true model. This is the parameter of interest that we're trying to make inference about. Then we have the data that comes from a simple random sample of size n. We have a method with which we analyze this data, or the method that we expose the data to. K represents background knowledge we have as scientists, and D is some constants that we may need to introduce ourselves, some pre-parameters like the, in hypothesis testing framework, we set the alpha level ourselves, for instance. And that also allows us to define what is a replication experiment. Now that we know what we mean by a study, a replication study needs to be different from an original study in some sense. And we show exactly how it's different. It is different in the background knowledge because the replication study comes in with some existing knowledge about the original study. So the background knowledges are different in both cases. And also we use an independent, simple random sample. So we have different data, basically. I'll go back to main slides. So as a result of laying this groundwork, we are able to define one of the concepts that is necessary to us. Now we will continue building on this foundation. So let's take our first claim that reproducibility is demarcation criterion for science. Here are two examples that I'm going to show you as to how common this framing is to understand reproducibility. The first one on the left that comes from a conference announcement from last year by the National Association of Scholars, which is different from National Academy of Sciences, so don't confuse them. But this conference, Fixing Science, happened last year, and I'm just going to highlight this phrasing here. If you cannot reproduce a result, it isn't science. This is a patently false claim, and we're going to discuss why and how we know this. This one from the Vox article is from 2 days ago, October 14th, and they use a very similar framing here. If I'm just going to read it verbatim, if they find the same result, that's a successful replication and evidence that the original researchers were onto something. But when the attempted replication finds difference or no results, that often suggests that the original research finding was spurious. So, which again is a false claim, and I'm just going to discuss how we know this. Based on our earlier definitions of an idealized study and the components of an idealized study, we can use probability theory to derive our first result, which says that the reproducibility rate is a parameter of a population of idealized studies. Basically, given a result, the relative frequency of reproduced results of the same kind approaches to the true reproducibility rate that lies between 0 and 1 of that result as the number of studies increases. So we have a population of studies that we sample from, and from this population of studies, we derive results. So there's a distribution of these results. And based on that, we can talk about a true reproducibility rate. Thus, the reproducibility rate is a parameter of the population of studies. Further, the true reproducibility rate is 1 only for trivial results. Because we work in a stochastic setup and not in a deterministic system, we can never achieve 100% reproducibility. Let me just show you how this proposition looks in the math. So we have a proposition and we have the proof of this proposition that follows from first principles like the definite series representation theorem and the strong law of large numbers. I'll go back to the slide. And for a simple example of why or how we will never have 100% reproducibility rate in stochastic systems, I would recommend one book, Inventing Temperature by Hasok Chang. It kind of talks about the history and philosophy of science of how temperature was invented. In that book, it's a wonderful book I can recommend for many reasons, but there are examples of a lot of experiments in control settings where the known boiling temperature of water, which is 100 degrees Celsius, could not be observed. So this is in controlled experiments, and we're talking about, like in chemistry and physics and even then, we do not get 100% reproducibility because there are a lot of variables that's affecting what's going on, and there's a lot of variability in results. So now, next, what we need to do to address the claim about the demarcation problem is how do we formalize the demarcation problem? That's a little bit more of a challenge because then we need to be able to figure out a way of formally state what we mean by demarcation, which is practically a philosophical statement, not necessarily statistical. But in this case, we're gonna try. So we break the idea of demarcation down into two complementary propositions. One about the reproducibility rate of true results, and another about the maybe irreproducibility rate of false results. And provided proof like this again. We have two propositions and a proof that establishes basically two facts: that true results may be perfectly irreproducible. So we're not talking really like sometimes reproducible. It may be perfectly irreproducible, and we can have false results that are perfectly reproducible and under given circumstances. In this box, I took it from the paper, but I compressed it a little bit because it had a lot of examples. So I took them out. You can find it in the preprint. We establish some necessary conditions to obtain true results that are reproducible and false results that are not reproducible. So to be able to meet this demarcation criterion, you need to satisfy at least these conditions, and maybe some more, because this is not necessarily an exhaustive list. I'm going to just highlight a few of these just to, I'm going to make a specific point about that. Let's take the first one: true values of the unknown and of unobservable quantities for which inference is desired must be in the decision space. What does this mean? This is typically referred to as, in technical terminology, enclosed model space. That is, we need to be operating in a system where we actually have access to the true data generating mechanism. As scientists, we don't know the truth, but we're considering certain options and alternatives, and we have our own models of truth. But if our own models of truth do not capture the actual truth, like if it's not somewhere out there that we can reach, we're never going to be able to access it. Hence, we're never going to have reproducible results that are true. One step further, even if we have access to the true model, we need to be making inference under the true model. In every other case, we are making inference under model misspecification, which is the most common thing for the sciences. But under model misspecification, a lot of things can go wrong. One example of that is making inference under measurement errors when you don't know that you are making inference under measurement error, so you have not accounted for that. I'm going to give a very detailed example of this one. I'll jump to one of the later ones here about the free parameters of methods. So imagine that we're operating in a Neyman Pearson type hypothesis testing framework, and we have to set our alpha level, the type 1 error rate. Typically, we set it to 0.05. That's not a magical number. There's nothing specific, special about it. It's just a heuristic. But I could just as well set it to 1. There's nothing that tells me what level alpha should be other than my own goals as a researcher. I could set my alpha to 1, which will still give me a valid test, valid in the sense that the test will do what it was supposed to do, which is it's going to reject the null hypothesis every time whenever it's true. So I'm going to have a perfectly reproducible result that is false, because I set my free parameter that way. Another example that we should have methods that are free of unknown bias, think of the observer effect, where observing something changes its nature. Well, it's very interesting example of that is something called the Heisenberg bug. If you haven't heard that before, it's a software bug that disappears whenever you're trying to debug it. So in the debugging mode, you cannot observe it. As soon as you go out of debugging and you're trying to use the software, it starts bugging you again. So that is a special case of the observer effect. What I want you to take away from all of these examples is that the reproducibility rate of a result does not only depend on the truth. So even if you may be making inference under the true model, but still every other component of the idealized experiment that we defined is going to have an impact on whether your true results are reproducible or forced results are irreproducible. From the background knowledge that we have about the subject, to the model we are making inference under, to the free parameters that we set, or to the methods that we use, every single component is going to determine whether we can meet this demarcation criterion. In all likelihood, in practice, we will never have this kind of luxury. And there's never going to be a one-on-one mapping between reproducibility and discovery of reproducibility and a true discovery. So I want to discuss one specific example in further detail to explain what would happen if we were to use the reproducibility as a demarcation criterion. On this slide, the plot that you're looking at is titled Reproducible Rate of False Results under Measurement Error Model. So imagine we have a research question about the effect of a predictor on a dependent variable. So we're operating in a simple linear regression framework. However, let's assume that we have a problem in our measurement instrument that it records things with some kind of noise. So it adds measurement error. But we do not know that. So think of, for instance, the scale that you step on. Every single time it gives a different measurement, but instead of thinking that the scale has measurement error, you think that, oh, I maybe put on some weight, or I ate a little bit too much today. So you're not taking that into account, that it could be the measurement that's problematic. So what we're looking at here in this plot is that a lot of regression analyses that we simulated. So on the x-axis here, we have a ratio of measurement error variability to sampling error variability. Sampling error variability is the regular variability that you would expect in your dependent variable. And the measurement error variability is added noise due to the error in your independent variable. Normally, in a simple regression framework, the independent variable should be fixed. In this case, it's not fixed, but we are treating it as if it is. The larger this ratio, the higher the effect of measurement error in your results. On the y-axis, we show the distance of our estimated effect from the true effect. So closer to the origin, we are closer to the true effect. As we get higher up in the plot, we're getting away from the true effect. Every point on this map represents the summary of results from a million simulated regression models based on independent samples of size 100 observations. So this actually is a summary of a huge amount of data. For example, what does it mean when we look at this point F on the upper right corner in the plot? It shows that we have very high levels of measurement error variability as compared to sampling error variability, and we are very far away from the true effect. So what does this heat map then show? The heat map shows the rate of reproducibility. So the darker the color, the higher the rate of reproducibility for that particular result. So again, if we go to point F, it is on this black band, which means we're around 100% reproducibility for that point. So now imagine I'm a scientist doing one of these experiments, and I end up at this point A. And also imagine that I use reproducibility as a demarcation criterion. So if I cannot reproduce a finding, I'm going to assume that it's false. If I can reproduce it, I'm going to assume that, okay, like this is a good sign. I'm about to make a discovery. So I'm at point A, and I look around, I retest the study, man, I can never reproduce it. It's basically 0%. So what I can do is maybe I'm just gonna tweak some of my measures, like the remeasure the independent variable, change something, and I end up, say, at point B with my new measure. I have actually, in fact, I have added measurement error variability, but I don't know that. The only feedback that I get at this point B is that, oh, now I'm in this like a light blue region, which maybe corresponds to 50% or 60% reproducibility. So that's the feedback I need, tells me that, okay, I did something right. So I can do a little bit more tweaking in the same direction, and that might land me on point C. On point C, I get toward the darker region in this plot, which corresponds to, again, 90 or 100% rate of reproducibility. If I move a little bit further in the same direction by making more tweaks to my measurement, I'm going to end up in one of the lighter regions, which will tell me, okay, go back, C was a little bit better. So C will become my stable equilibrium. Notice that all this while, I have not gotten any closer to the true effect. I am at the exact same distance, I'm not getting any closer, but I'm getting reassurance that I am getting closer. So I'm getting a false signal. Another scenario could be that maybe I did some other tweaking, and with this feedback mechanism of did I reproduce it, did I not reproduce it, I end up on point D. That's possible as well, which because, I still end up with 100% reproducibility, but now I have actually moved farther away from the true effect that I was interested in. The problem with treating the rate of reproducibility as a demarcation criterion then is that it does not help me move in the direction that I actually want to move. I need to be making a vertical move to get closer to truth, but the feedback that I get is moving me on this band instead. And it could be anywhere, because with that metric, I cannot tell the difference between point E, which is close to truth and 100% reproducible, and point F, which is the opposite of that, basically. So we need another mechanism that will help us move in this other direction, in the vertical direction, and rate of reproducibility is not that. Remember that this is only one of the possible illustrations. This is only a special case of one of the points that I showed on box 1. There are many other similar conditions that might end up reinforcing results that are not aligned with our original goals as researchers. In conclusion, a formal evaluation of this claim, I just put the claim here as a reminder, tells us firmly that reproducibility cannot be a reliable demarcation criterion. And if we aim to optimize rate of reproducibility, aim for always getting higher reproducible rates, it may actually end up moving us away from true discoveries, unless we know why we're getting these high levels of reproducibility. And it may end up getting us stuck at a false consensus. Maybe then, instead of using these ideas as metrics without really understanding them, we can ask better questions. Maybe we can ask, how can we take this idea of an idealized experiment and use its components to design better studies that will help us move in the vertical direction, and that will help increase the probability that we're going to make true discoveries. Or we can also ask, what's the best way of learning from replication studies? If it's possible that we can replicate false results, what is the information of a replication study? What can we learn from that? And that requires more theoretical work in the same vein as our work. So, okay, let's take a deep breath before I move on to the next claim. I know this is a lot of technical information maybe, but hopefully the core point about why we can benefit from this kind of formalism is coming across. So the next claim may be a little bit more contentious even, because it's typically accepted as an uncontested fact by many scientists across many disciplines. This claim is about this idea of using data more than once invalidates statistical inference. That sometimes also referred to as double dipping. Sometimes it's referred to as peeking at data before you make statistical inference. One of the seminal meta-science theses on this is Logan Marcus et al. 2012. I'm going to use a few quotes, and the piece is called An Agenda for Purely Confirmatory Research. I'm going to use a couple of quotes to illustrate the point that they're making. Whenever a researcher uses double-dipping strategies, type 1 error rates will be inflated and p-values can no longer be trusted. They add further that at the heart of the problem lies the statistical law that for the purpose of hypothesis testing, the data may be used only once. So the first statement is presented as an unconditional fact, which is basically what makes it false. If it were qualified, if the assumptions were clearly laid out and may have been correct under certain circumstances, but it's not clear from the paper or anywhere else from the literature. The second statement, from my perspective, is a little bit unfortunate because there's no such law. They probably wrote that in jest, but it does come across as uninformed and it's misleading. So from our perspective, especially methods reform, since it came against similarly sloppy practices, it should refrain from these overgeneralized statements without providing the work for it. So how can we formalize this idea of double dipping? What does it mean in statistical terms? Let me try to illustrate that with a very simple example. So imagine that we are interested in a mean treatment effect for an intervention. So specifically, we want to test whether the population mean of an outcome variable for treatment 1 is larger than the population mean of an outcome variable for a treatment 2. We will employ a very simple two-sample z-test, and our distribution of our test statistic is given with the black curve here, and the test statistic here captures the mean difference, the scale mean difference between two different samples. And for error control purposes, we want to set the alpha, say, to 0.05. That's what we fix, and we do that by calculating a critical value beyond which we're going to get 5% area under the curve. So the critical value we calculate under this black curve is z, is given by z, and the critical region is the sum of black and brown areas, basically. So in this case, all is in order. We can just go with the test, and this is going to help us maintain our error rates. Now in this problem, let us introduce some double dipping. How might that look like? So maybe I want to, before I run any hypothesis test, I may want to do some exploratory analysis. I'm just gonna look at some histograms or some scatter plots, and I want to see, before I run the test, that the sample mean 1 is actually larger than sample mean 2. Only if we can show that the sample means are already different, I'm going to go with the test that I planned before. So far, there's still not a problem. I can do that. Looking at the data, exploratory analysis, trying to be familiar with the data, it's all good practices. what may be a problem is basically what I'm going to do next. That will determine whether I have a valid test or not. So because once I conditioned my decision to go with the test on the results of my exploratory analysis, because I said that if I observe this, I'm going to do this test. If I don't make this observation, I'm not going to do this test. Now we have a conditional distribution of the test statistic, which is shown by the orange curve. Basically, it says that I have changed by conditioning the decision to do the test on my exploratory analysis. I have changed the sampling distribution of my test statistic. Now I have, instead of a normal curve, I have a half normal distribution, which does not allow my test statistic to take values below 0. I have canceled that part of the test. Now all of the probabilities are distributed on one side of the curve. So if I don't take into account and I continue acting as if I did not change the distribution, I'm still going to be using Z as my critical value. Let's see what that does to my test. You go up, look at the actual probability distribution of your test statistic. You will find that we have increased the size of the area, the shaded area in the critical region. We have practically doubled our type 1 error rate. So this makes it an invalid test. So this is what Wagenmakers et al. Are talking about in the first quote. Okay, yes, we have changed our, we have inflated our alpha, our p-values don't make any sense anymore because we are making inference under the wrong probability distribution. However, there's a fix for that. If I know that I have conditioned my decision on a previous observation, now I can drive this conditional distribution. In this case, it's half normal. It's not always going to be as straightforward, but theoretically you can do that. And it's going to give me, I'm going to calculate a new critical value, which in this case is given by Z star. And if you look at this, Z star lies further right than Z, which gives me a larger cutoff. So it will be more difficult for me to reject this null hypothesis. And the new critical region is given by the sum of these two areas shown by orange and brown colors. So either one of these tests, either the original one that uses Z or the conditioned one after exploratory analysis are valid tests. The only one that's not valid is I make the conditioning, but I do not implement that in my test. That's the actual problem. So what we learned from this is that the problem is not necessarily double dipping itself per se. So if we summarize what we find, what we learn from theory in this proposition, if performed properly by adhering to probability calculus, using the data more than once does not jeopardize the validity of a statistical result. Further, using information from the data to modify the procedure of inference might even improve the properties of statistical procedures in these cases, in a lot of cases. So the proposition has two parts, and we have a couple of proofs that we show in the paper as well. Pretty much the proofs follow from the well-known Rao-Blackwell theorem in this case. But again, I'm not going to go through those details. But I'll show you a little bit more extensively what we find to give you a little bit better picture of the main result here. So this table is a summary of a major and extensive statistical result that we have. And it's, as you see, it's titled The Effect of the Information Gathered Prior to the Test of Interest on the Test of Interest. So the rows here represent the information we gather in our exploratory analysis of the data. And we assume that all the information that we can capture from exploratory analysis, we can summarize in a statistic. So that the rows represent the different types of information we can capture from our exploratory analysis. Sometimes, like we do exploration that has no bearing on our subsequent analyses, so it contains no relevant information. Sometimes we're going to do extensive exploratory analysis that contains all the information that we need to determine what we're going to do next, or that is related to the information that we're going to use in our test of interest. The columns show that our original test of interest, and they represent the type of information we need to use in the actual test of interest. We're looking at when we need to update the sampling distribution of our original test statistics based on what we learned from prior analysis. The boxes on the left are a little bit of a subset of the cases that we discussed, and it's not necessarily a lot of time what comes to mind when people are talking about double dipping practices. But still, it's important to understand theoretically what's the difference between them and how the theory clarifies when it is safe or even useful to do this kind of double dipping. So in these cases, the left block, we do exploratory analysis, we'll look at the data, we get a lot of information, but we do not use that to make any decisions as to the following analyses, the test of interest. We are going to do what we were going to do anyways. We just want to be more familiar with the data beforehand. In those cases, it's typically not necessary to do conditioning because our decisions have not been affected and the distribution of our test statistics is not altered because we did exploratory analysis. However, in some of these cases, it might actually be useful to be doing the conditioning. So for instance, our exploratory analysis captures a lot of information, whereas the test that we chose did only contain partial information. In this case, we need to be doing conditioning. It's unnecessary, but it always improves inference. So in the appendices of the paper, we show exactly what, when, and why this works, statistically speaking. But the box on the block on the right probably is of more interest, and it captures a lot of the cases that are referred to as double dipping. This is when we look at the data, make some decisions, take some turns in, like forking paths. We decide which path to take based on what we see in the data. In this case, problems arise when you do not condition. Well, not always. We also show that, it's possible that your decision actually would not have mattered based on what you saw because the exploratory analysis actually contains no relevant information to your analysis. In those two cases, bottom right, conditioning might be necessary for valid inference, but it's you decide that on a case-to-case basis. It's not always necessary. But in a lot of cases, as long as the decision that informed what you're going to do next involves some, at least partial information that is relevant to the analysis that you're conducting, you need to condition. A lot of these cases, it gives you a valid test. In some cases, it might give you not only a valid test, but your test will be improved by doing the conditioning as opposed to not doing exploratory work beforehand. So the summary of that, a lot of this is actually, I tried to hold back some of the technical words, like what we mean by contains all the information is complete and sufficient statistics, which contain information about parameters, interest, and everything. So I did not want to go into too much detail because time concerns and everything. But the takeaway from this, from our perspective, is that outright banning of double dipping is problematic for various reasons. First thing, it really obscures the actual problem. It makes it look like the problem is exploring the data, which typically is a recommended practice. You need to be exploring your data before you fit any models to it. You need to be understanding what it looks like, what kind of problems is there in the data. So it kind of creates this false alarm about looking at the data. Looking at the data is not the problem. The problem is that you need to be doing conditional analyses. The second thing is it might actually prevent better analyses. Like in some of these cases, we can improve inference by doing the conditioning. If you never do exploration, you won't have that chance. I think one of the problems we're having with this kind of approach, the heuristic approach, like do not do double dipping, it's bad, is that it turns statistical inference into some kind of black box, and like a combination of a black box and the heuristics, which it is not, because we can specifically say under which exact assumptions what analyses are valid and not. And instead of like creating a path to understanding how these things work and the mechanism behind it, kind of obscures what's going on. So one of the policy implications of double dipping has been, in the reform literature, has been about pre-registration and how it relates to statistical inference, because pre-registration has been oftentimes presented as a safeguard against double dipping practices. So now that we understand the mechanism, we have a definition for what double dipping is, we can give very clear and not our argumentational but factual answers to some of the questions about pre-registration. So can pre-registration solve problems related to double dipping? The answer is no, because problems are not one of double dipping. Problems is about proper conditioning. And pre-registration is not necessarily a guarantee that you're going to be doing conditioning the data, your analysis the way you should. Can pre-registration, strict or flexible, we did sort of this take on pre-registration, because some people take it as strict, that once you put it on paper, you're going to have to follow through. That is, of course, kind of a misconception maybe of pre-registration. So there's this idea that it's not a prison. You need to be able to get out of a pre-registration if you see a better path for data analysis, for instance. Can either one of these approaches, either strict view of pre-registration or a flexible view, harm validity of statistical inference? Yes, for both cases. And in the paper, we provide another simulation example. If anyone's curious, you can just read that in detail, where we look at multiple scenarios of cases with pre-registration or flexible registration or no pre-registration, and under different distributions. So if you're interested in more examples, more applicable examples of pre-registration, it's again in the paper. But our answer is yes, in the sense that strict pre-registration may not allow you to engage in exploratory analysis that you should be engaging in, and a flexible pre-registration may leave you too free, and it may not guarantee that you're going to do the conditioning as you should. So either one is not necessarily a solution to the problem here. Can pre-registration then make statistical inference valid? No, because statistical inference is only valid when you abide by its assumptions, when you follow the procedures, when you can derive the right sampling distribution for your test statistic, and when you know what you're doing. Pre-registration is not necessarily a safeguard against misusing statistics. Does it serve any other purposes? Of course. I mean, it gives you transparency of procedures and the processes that you use. It gives you a way of document what you did. And it can even serve as kind of an external memory in case you tend to forget what you do with your data. And it could even serve a social signaling function to other scientists that, like you laid everything out and they can check your work against it. So it does have other uses for sure, but we cannot say that it's a statistical tool. So in conclusion, if we reevaluate what we find about claim 2, that using data more than once invalidates statistical inference, that it does not. Including hypothesis tests, we can do double dipping. There's a right way of doing that, and there's a wrong way of doing that. Outright discouraging data picking may actually harm statistical inference in the sense that it may prevent us from doing better analyses. Recently, I just came across this preprint a couple of days ago on arXiv, written by 2 statisticians. It was one about whether we should be testing model assumptions before model selection. And the literature about that has been also contentious, and they do a whole formal analysis, evaluation of the problem, and they come up with the answer, yes, we should be testing our model assumptions. And if you think about it, testing model assumptions is one type of exploration, one type of data picking. And they also go around showing that by using the same theories that we're using, that it's a conditional analysis, basically. If anyone's interested, I can send you the link to the preprint. And third, what we learned from this claim is that registration is not a statistical tool and cannot control for statistical validity. So whenever we're making claims about these tools, we need to really properly assess what they are capable of and what they're not capable of. Only way to use statistics right is to statistical expertise, basically. You need to know what you're doing. You need to know what your data is like. You need to know the assumptions of every single statistical procedure that you're using. So the next claim, I'm going to discuss the last claim, but I'm not going to offer a formal analysis about it, but I'm going to discuss why formalism is difficult in that case and why it actually matters from the perspective of methodological reform. This claim, kind of the figure I took from Wagenmark as well, the same paper, but it has had already a lot of impact. The figure has been reproduced in a lot of different articles and blog posts and elsewhere. And this idea that we need to separate between exploratory research and confirmatory research based on statistical grounds. And whenever we're using wonky statistics, we have exploratory research, has been very impactful. We see the same argument repeated in a lot of different publications after this. The authors give a sense of what they mean by wonky statistics here. It's that in the gray area of exploration, data are tortured to some extent, and the corresponding statistics is somewhat wonky. So I think we can all agree that it's not misusing statistics by violating their assumptions or using the test statistics, using the wrong sampling distribution. That cannot be a sound scientific practice for whatever purpose, whether it's confirmatory or exploratory. We cannot recommend scientists to do that. That's why we have an issue with this whole representation of exploratory research. There is no way we can theoretically show that misusing statistics or torturing the data is going to help us make true discoveries. That connection cannot be made. It's possible that it is going to promote a lot of false discoveries, but that's not what exploratory research is about. Exploration is about actually making true discoveries. We cannot achieve that by misusing our tools, whether it's statistics or anything else. So to us, making true discoveries, exploration has a huge part of the scientific method, and it has an important place, and it should have an important place in scientific progress. A few days back, I had this meeting with biologists. wanted to do something on the scientific reform, wanted to write something up because she was thinking that some of this rhetoric around exploratory research is hurting one of the most exciting parts of research, and people were starting to get scared to do exploratory research because it looks like, you know, it's a bad thing. It's a second class type of work. It's not that. Exploration is much bigger than actual data analysis, but also the difficulty that we had in approaching this issue is that it's very hard to formalize. What is exploration? How do we formally define it? It's not an easily quantifiable process. Exploration is typically associated with hypothesis generation. Bertrand Russell famously said that the hypothesis generation is the most difficult part of scientific work, and he even said that no method has been found which would make it possible for us to invent hypotheses by rule. So suffice it to say that we did not make that happen in this paper either. We tried to come up with a logical and formal definition. It's not happening. This is by Charles Peirce. It's referred to as abduction proper. And it's not an easy job to actually reduce it down to a statistical model. Formalizing would be a whole research stream, and I think it's a very interesting issue. What we know, however, is that the exploratory confirmatory distinction is not something we can reduce down to whether we use statistics right or wrong. That, I think, misusing statistics should not be recommended for any purposes. Exploratory research should be taken as seriously as confirmatory research, and the goal of exploratory research should be to increase the probability of making true discoveries and to be able to separate them from false discoveries. We need methods that will allow us to achieve that.
Berna, we're just to make sure we have discussion time. Could you just wrap up in the next kind of minute?
Okay, I'm just like one more slide conclusion.
Okay, cool. Thank you.
All right, sorry about that. I had timed this, but maybe I talked a little bit too much. So, okay, in conclusion, our conclusion is that we need statistical rigor and we need nuance in the claims that we make in methodological reform. So we need to move away from speculative and unfounded claims, sweeping over generalizations. We need to really aim for precision and clarity, and formalism allows us do that by laying out clear definitions, by laying out our assumptions and showing our work with proofs. We need to be developing robust tools and methods by using statistical theory, and we need to be systematically testing and extending these tools. Remember the central limit theorem example. And we should not rush to implement new science policies based on these methodological suggestions before we know what it is that we're actually recommending. And one last word that I would like to leave you with is that we need to remember that not all impact equals progress. Remember the p-value band and what happened afterwards. We don't want to be moving in a direction that is going to take us back. Thank you very much. Sorry for taking a little bit extra time.
That's fine. We start a bit later.
I can take questions now.
We'll have a virtual round of applause.
Thank you.
It's always a challenge to go a whole hour. But yeah, if people want to kind of show their video or clap, please go ahead. It's always nice for the speaker to see more than just their face. But yeah, I will open the floor up for questions. Sorry, I'm just going to pull up all my windows. I would particularly encourage ECRs to join in the questions, and I'll try to prioritize those earlier on. While people are thinking about their questions, well, I've loads, but I was just wondering, going back to the beginning of the talk around replication. You know, you talked about replication as being a cornerstone, as seen as a cornerstone of kind of science and finding the truth. And naturally, the word of a cornerstone already means that there's more than one. You know, there's to have a corner, you need two or three, I guess three, if we think about it. And I was wondering who in the academic literature actually kind of says that if a result reproduces, it's true, and if a result doesn't reproduce, it's false, because kind of the two examples you showed, the first, the NAS, like I did a lot of work with Dorothy Bishop on this. It seems to be a kind of right-wing group, while Vox is a media report. So I was wondering, I haven't really come across this argument. I was wondering where you'd seen that.
I see. So I need to kind of maybe go back to the paper, but I think the idea is it starts with, well, maybe in the replication crisis, the idea starts with the original reproducibility project by OSS. There are statements in that regard in that paper, and the demarcation quote actually is repeated in that paper, but originally was from another one. And just because that one paper has been so impactful, now I see the exact same argument repeated. Kind of, I think it's mindlessly repeated. People may not necessarily think about it carefully when they repeat that, oh, yeah, we need to have reproducible results. But I think after that original reproducibility project, psychology, I saw the same argument in a lot of papers that have cited it. But I have a few more citations in the paper for that, but I did not include like an exhaustive list. But it comes from that paper originally.
Discussion, sorry, my internet lags. But in discussions with students, they often already see that if a result, doesn't reproduce, that doesn't mean it's false. And if it does reproduce, it doesn't mean inherently that it's correct. It's just that we need to do more exploration. And I felt that that linked in with your measurement picture, because there it was all about measurement quality. And again, isn't it all about robustness of results, and like that it just gives us an indication we need other measures of quality as well, not just reproducibility?
I'd say the thing is that measurement-error example, as I said, is only one example. It doesn't necessarily have to be measurement error, but of course we need to be testing the robustness of our methods and everything. But even then, I think the idea that we have is, even if you can regularly reproduce a finding, and with that, I see the way people talk about results and when replications succeed is that, okay, it's a fact, we know this because it's been replicated. And how many times is enough? It's not a matter of how many times we replicate something. It's a matter of actually understanding the phenomenon and understanding why it replicates. It might be replicating because of model specification, might be replicating because of methods related artifacts. Maybe it's a measurement issue. We need to, I think the whole reason that I switched to meta science was because I wanted to theoretically understand what reproducibility is, what are the dynamics driving it, and it's not just the truth. The whole point is that it's not a function of truth. I mean, it is a function of truth, but not just the truth. And we need to be studying these dynamics a little bit better to understand why, for instance, in a given field, let's say in specific literature in social psychology, if a finding replicates, why does it replicate and what does it mean? And we need to be thinking about those processes a little bit more carefully. I think it all comes down to how formalism can help us appreciate these mechanisms and the complexity of these questions. It's not like I have an exact answer to why something replicates or doesn't, but I think we need to be asking these questions and not take the replications or replication failures at the face value, and not just in the sense that, oh, okay, of course, there's sampling variability. There's much more than sampling variability is the point.
I muted. Oh. I did the classic muting yourself. So if anybody has a question, please raise your hand or put it in the chat or button as well. I had one in the chat early on by Keith Lang, who said, could you please provide the reference for claim 2? I think that was claim 2 about pre-registrations. Is this the value at all 2012?
Right, yeah, Wagenbachers et al. And there was actually a similar claim that we cited, phrased a little bit differently from one of the Mosaic papers, but I forgot which one. I can share the paper though. If you email me, yes, I can just share the link. Okay, actually, I want to leave on this slide just so everyone has access to these links.
Great. Any other questions? If not, you'll have to endure me asking you another one.
Sure.
Tristan, you're going to go and then I'll go again.
Yeah, I mean, maybe we'll kick off the discussion, because you at the end, because we said, wrap up. You said, well, actually, there are a couple of good things of doing a pre-registration, right?
Right.
And one thing that I've been sort of pushing for the department to do is for the last year projects to make the student pre-register what they're going to do. But the underlying reason of that is not, it's to learn, right? It's a training reason.
Yeah.
So I actually, when I was reading your paper in April, I was a bit surprised that to think that the claim for the pre-registration was a statistical claim mainly. And I sort of disagree with you when you say, well, I don't know, but I don't pre-register for the statistics. It's just like, yeah, of course it helps, but is this something you encounter, like systematically when you give
we did.
as the people?
It's part of one of the arguments. It's not I think it has evolved quite a bit, to be honest. At first, I saw this a lot. A lot of people were pushing for registration because, it maintains the validity of your statistical tests. And then, there has been a lot of discussions. At some point, there was this, what's the word for it? I was involved in a project that went nowhere. It was supposed to be an adversarial collaboration between people who had different views of pre-registration. And my view is that, it has different uses, but it's not a statistical tool. And there were a lot of people very vocal about using pre-registration for error control purposes. It just maintains your type 1 error rate. I don't necessarily want to name names because they may have changed their minds, but the idea is out there for sure. I came across it in papers, but also in informal discussions a lot. And that's something I think we need, that clarity, that what it can achieve and what it cannot achieve, and not necessarily take these tools as a cure-all solutions to the problems that we have. I think it's not a straw man. It's just part of the argument that was presented to support pre-registration. And now that there are better arguments out there.
I'm just going to open my participants again. Susanna?
Hello. So I'm
Hello.
in the psychology department at Anglia Ruskin, and I have some colleagues at Cambridge, so I'm joining. So thank you very much. That was incredibly interesting.
Thank you.
I confess I'm not as mathematically able as you are, and I think I probably didn't catch a lot of the subtleties and the proofs there. But I wanted to just respond to a comment that you made, which is that if we to say that double dipping is not an appropriate practice is to kind of treat statistics as a black box, and to say that certain practices are okay if done in the right conditions and not okay if done in the wrong conditions, and it's a sort of don't look inside the box.
Yeah,
that's a very familiar argument, and I think we've had a lot of discussions around statistics used inappropriately for exactly the same reason, which is that scientists don't really understand what they're doing when they're using statistics, and use them sort of fairly clumsily, a sort of rote learned process that they've read in a textbook, they were taught as a student. Is there a way that we could teach our students and teach ourselves that would be more appropriate, short of us all having full degrees in statistics, which clearly would
right,
be
right,
the ideal solution.
yeah.
How do we approach this problem space of falling back on treating something as a black box because we don't understand what's inside it?
I think, well, that's an important question, and it's a very difficult question to answer. I'm just going to give you an example, personal example. I have a master's in statistics, but my PhD was not in statistics. And a lot of the formal work you see here, I could not do on my own. I may have my intuitions a little bit more aligned with how statistics works, but if it weren't for collaborating with actual statistician who does theoretical work, I could not have done this on my own. So first thing, I think collaboration is key. Like this may be in some fields, I think it's more common that we should be jack of all trades and do everything on our own. I don't think it's conducive to better research and better science. We cannot do everything well. From the student's perspective, I think instead of trying to teach like statistics at a theoretical level to all graduate students in all fields, which is impossible, probably should be sharing conveying the idea that things are complicated, and a lot of the heuristics that we use may have some truth to it, but they're conditional. They work under certain assumptions, and at the minimum, we need to get familiar with the assumptions we are operating under, and make sure that the heuristics that we use are aligned with what we're trying to achieve, and we're not really borrowing heuristics from everywhere because they sound like easy and doable. But beyond that, I think, so let's just take that idea of doing conditional analysis for double dipping. And when you have a case like normal house normal, which is very simple, it's easy because you have an actually derived, ready to go distribution for your test statistic. It's not going to be that easy with real life problems. Our point is that there's a way of approaching that. It requires a lot of work. That's not easy. We cannot do that like overnight. It takes a lot of work to think through these problems, and we should be thinking about them or collaborating with people. And I kind of would like to invite Erkan if he wants to add to that, you know, like how to teach specific skills that will enable people to maybe employ statistics the right way. And I don't know whether Erkan is still.
Yeah, I'm here. I'm
okay.
here. I mean, I agree with Berna 100%. And there's a job as called consulting statistician. And biologists would often do this. They would just go to the statistics department and they will collaborate with consulting statistician to make sure that their methods are working properly, or they would just present the problem and ask for a statistical inference solution. And I totally agree with Berna. It's hard. I mean, one thing I have been looking at this, talk and just thinking, how would people in a psychology or cognitive science department feel if, as a statistician, I come and say, hey, consciousness is like this, like I'm a statistician. I know nothing about psychology, but here is what I think about consciousness. So the methodological arguments that we hear from reform literature are sounding very, they are not based properly. You see, like they are not shown properly in terms of the proofs and the statements. And I think it's the collaboration is the answer to this. And, not all statisticians would do practical work or consulting. Some of them are more theoretical and they would be just driving results from a probability theory perspective. And so they won't be the collaborating statisticians, but a lot of them also do practical work in terms of their field, like epidemiologists collaborating with epidemiologists or biologists, geneticists. My own PhD is in bioinformatics and computational biology, so I'm collaborating with them very often. I guess it's the finding the right person is the answer to this.
Yeah. Okay, thank you. That's really helpful.
Thanks as well. I think it comes back to, I was recently discussing with a grad student how we need to ask for enough money to do our science well, and we often don't, especially in psychology. Kind of, you know, we don't have the stats consultants. And I guess this then the last question when we wrap up. In a way, we are then left with this very uncomfortable situation that we are uneducated. You know, we're not educated enough to, for example, create these conditioning statistics, especially at an early graduate level when we start research. And we often don't have the stats training to condition maybe properly. And I've been trying to follow all the technical parts of your argument, and I printed out the paper, and I'm still struggling as a person who is quite technical in the field, so I was wondering, I was just thinking in like a kid's playground, we often have safeguards, you know, we often have extra safety measures. And do you see that maybe something like pre-registration is a safeguard in that, you know, in that situation where it's not ideal, we shouldn't have to have this, but because we are not training to that extent and we don't ask for enough money to hire the statisticians, that we might have to?
I need to think a little bit about that. Of course, we need to have safeguards, and that makes a lot of sense. The problem that I have with turning these safeguards into heuristics is that then it becomes an established fact, and people do not look behind that. So that's why I think like pre-registration, I'm still not convinced that it might help you do the right analysis. You know, it might help document that you did the wrong analysis, you know, like it's possible, but I don't think it's the right safeguard for statistics. But with regards to say, okay, I'm just gonna, as a researcher, I know my capabilities, I'm not that good at stats, I'm just gonna avoid double dipping. I think I'm fine with that as a personal decision. If this is your safeguard, if you know your limitations and you think that, you know, like if I look at something, I might be influenced by that. So I'm gonna use something as a safeguard that's gonna prevent me from doing the wrong thing. Should be your personal decision, but it should be an informed decision. And for that, you need to know what you don't know. And I think turning things into like, okay, double dipping is wrong, prevents you from making that informed decision. And it kind of pushes you to make a decision out of fear, and it prevents you from learning more about it, even knowing that there's more to learn about it. And there's always more to learn about it. So I think it's important that we kind of scale back our claims a little bit, you know, like do not make these sweeping generalizations. We don't need that. Lay out the risks to people, lay out, you know, like what they could get wrong and the complexity of the issue. The oversimplification of these issues, I think it's a bigger problem than the issues themselves even. So like, it's complex. There's a lot that we don't know. As I said, there's a lot that we don't know about reproducibility and why we are able to reproduce something. I can, as you mentioned at the beginning, I come from an experimental background, and I wanted to know like why I was not able to replicate anything from the literature that I read, anything, like it never worked. I wanted to know what was the reason for that. And I still would want to be, I would be curious to figure out what's going on behind the scenes. So we should be asking the questions about, you know, what is reproducibility? What's causing it? And instead of just assuming, no, I can't reproduce, it's not a fact. So yeah, I think the whole thing, our idea is that things are complex. There are ways of attacking these complex problems. It's just, we don't have easy solutions. I guess it's science, you know.
Great, thank you so much. I think I'm going to echo, Deborah Talmy just wrote in the chat, thank you for your thought-provoking talk. And I think we had a lot of these, you said you're not following the chat, so we had a lot of—
Yeah, well, I'm reading it now. Like during the talk, you know, I get distracted. But.
Okay, well, I need to release everybody to their Friday evening and their weekend. But yeah, thank you so much for joining us. I think we have all the material we need for our reading. And this is definitely feeding into our discussions. So it's important for us to really think these things through. Great. Tristan, is there anything I need to do else? That's my last minute to host. So.
I mean, this will be the time that I start to say, hey guys, whoever wants to come for dinner with Berna, let's go, in the Chinese or whatever, but that's not happening. I'm trying to convince the department to give me the same amount of money we would spend to send, Amazon gifts to the speakers. I haven't yet gotten a response about it, but maybe it might come. No, I just wanted to say thank you for coming and opening the Zangwill on your sabbatical. Of course, it's just.
Thank you so much. Thanks for inviting. It was a pleasure to present it, and thank you all for listening. Yeah, and if anyone has any other questions, please feel free to email me.
I think they will, because I got quite a few sort of private messages in the chat saying, "Oh, I have to go. It's too late," but and I always said, "Oh, send her an email, and she might take some time. Send her an email, take some time."
Sure, yeah, definitely. Send an email, and don't be discouraged by the "I'm on sabbatical" automatic reply. I'm gonna get your email.
I think from a constructive point of view, you just destroyed the whole Amy's reproducibility, replicability to the. Talk she was going to do in the
it's still good work. I think we need to be having all these discussions from all perspectives. That matters.
Super. Thank you very much.
Thank you very much. Okay. Have a nice weekend, everyone. Thank you. Bye.
Ciao.